Today we're going to finish up talking about directional derivatives and the gradient. So we talked about a gradient of a function of two variables. So if we had a function z equals f of x, y, and if this were differentiable, then the gradient of f was a vector. It was a vector. The x component of the vector was the partial derivative with respect to x, and the y component of the vector was the partial derivative with respect to y. And if your function were differentiable, then it meant it was locally linear. It meant that the tangent plane did a good job of approximating the function. But beyond that, it said that if you understand the rates of change in the x and y directions, you pretty much understand the rates of change in all the directions. Because if you wanted to get the derivative in a direction, say u hat, you could use the gradient to do that. You would look at literally how much of the gradient was in that u hat direction, and that gave you the directional derivative. But one of the properties we talked about yesterday that the gradient has, because of this, because of the chain rule, is that the gradient of f at a, b is orthogonal to the level curve f of x, y equals f of a, b at the point a, b. So if we look at the surface and we slice it, and we look at f of x, y equals f of a, b, and we get our contour here, then what we know is that if I pick the point a, b, and if I look at the tangent line here, the gradient is going to be orthogonal to it. Right? And not only that, we know from properties of the dot product that the gradient is going to point in the direction of maximum increase. Okay? So what we're going to do today is talk about how this property generalizes to functions of three variables, and then what that means in terms of tangent plane. So we'll come back and revisit the whole concept of tangent plane. Okay? So any questions on this? Is this all good with your two-dimensional gradients? All right, so suppose f is a differentiable function of three variables. How would you define the gradient nabla f of a, b, c? What would go in the x component? So what would go in the x component here? So what would go in the x component of the gradient? Yep, fx. Just like before. What would go in the y component? Fy. And has been the tradition here in Calc 3, we understand what's going on with two variables. For the third, we just slap on a what? Just slap on that z. There it is. So in two dimensions, the gradient is orthogonal to the level curve f of x, y equals f of a, b at the point a, b. If we have a function of three variables, the gradient is normal to the level surface f of x, y, z equals f of a, b, c at the point a, b, c. And the proof of this is using the chain rule. just like we had seen before in 2 dimensions. We just tack on that third dimension. Okay, so what does that mean? That means if we have a surface defined f of x, y, z equal a constant. Okay, now was it on your take home we actually talked about this sort of situation when you had implicit differentiation. So if you have a surface defined like this, then the gradient of f at a, b, c is going to be a normal vector to the surface at the point a, b, c. So if we've got this surface here, f of x, y, z equal a constant, and I pick a point here, a, b, c, then the gradient is going to be a normal vector. And if I have a normal vector to a surface, that gets me the tangent plane. Okay, so this is another way to get the tangent planes. So, for example, consider the surface z e to the x plus 2y equals 1. So I can think of this surface as being the level surface of the function z e to the x plus 2y equal to 1. So I can think of this as a level surface f of x, y, z equals 1. Right? And so if I wanted the tangent plane, it says, well, prove f is differentiable by analyzing the first partials of f. So we'll prove it's differentiable. That means it's locally linear, and then we'll find the tangent plane. So to prove a function is differentiable using its partials, we look at the partials. So we need fx, x, y, z. I take the derivative with respect to x, in this case treating y and z as constants. So since z is a constant, I can move that out front. Now I'm taking the derivative of e to the something. The derivative of e to the something is e to that thing times the derivative of that thing. Once again, the derivative with respect to x. And the derivative with respect to x of x is just 1. What's the derivative of the y part? 0. Right, so there's my fx. And this is continuous. Right, it's built up of continuous functions, so fx is continuous. Now we'll move over to fy. That's the derivative with respect to y of z e to the x plus 2y. Once again, when I'm taking the derivative with respect to y in this context, I'm treating x and z as constants. Z can come out. Taking the derivative of e to the something, e to that thing, times the derivative with respect to y of that thing. And what's the derivative with respect to y of x plus 2y? Yep. So I'm going to get 2z e to the x plus 2y. And once again, this is continuous. And last but not least, let's look at fz. Here I'm taking the derivative with respect to z of z e to the x plus 2y. So I'm treating z as the variable, x and y are both constants. So that means that this whole thing, e to the x plus 2y, that whole thing is considered a what? Constant. So I just pull that out, and what's the derivative of z with respect to z? Yeah, it's just 1. And so this is continuous. And so since fx, fy, and fz are all continuous, f is differentiable. And now the fact that f is differentiable, that unlocks all the properties of local linearity and gradients that we had back in two variables. All right, so that's number one. Number two, find the gradient of f at negative 1, 1/2, 1, and use this to find the equation of the tangent plane of this surface at negative 1/2, or negative 1, 1/2, 1. Okay, so first off, if I look at this surface, z e to the x plus 2y equals 1, let's check to make sure that this point is really on it. So if I look at x, y, z is negative 1, 1/2, 1. If I plug that in, let's see if this even works. Z is 1. E to the x is negative 1 plus 2y. Does that equal 1? Well, sure enough, I get 1 times, what, e to the 0? So that point is on that surface. So that's always good to check to make sure you're looking at a point actually on the surface. Now we're asked to find the gradient of f. And the gradient of f is going to be normal to the surface at that point. So this is something we're going to, we'll use GeoGebra to check here in a minute. But let's find the gradient of f at 1, or negative 1, 1/2, 1. So by definition, that's the partial with respect to x at negative 1, 1/2, 1. The partial with respect to y at negative 1, 1/2, 1. And the partial with respect to z of negative 1, 1/2, 1. So now I go back to my partials. So let's go back to fx here. I want to plug in, I want to find fx at negative 1, 1/2, 1. So the x plus 2y, that would be a negative 1 plus 1. So that's going to be an e to the 0, which is 1. I plug in z is 1. So fx is going to be 1. Now let's look at fy. So once again here, the exponent, if I plug in fy at negative 1, 1/2, 1, the exponent's going to be 0 again. Z is going to be 1, so I'm going to get a 2 times a 1 times a 1. I'll get a 2 out from that. And looking at fz, at negative 1, 1/2, 1, get e to the 0, which is 1. Right? Any questions on calculating the gradient? So remember, the gradient is our normal vector. Okay? So we're going to write the tangent plane. The tangent plane has the gradient as its normal, and it goes to the point negative 1, 1/2, 1. So I need the plane with the normal vector 1, 2, 1, containing the point negative 1, 1/2, 1. So I go back to my formula here. I'm going to take the x component of the normal vector times x minus the x coordinate of the point plus the y component of the normal vector times y minus the y coordinate of the point plus the z coordinate of the normal vector times z minus the z coordinate of the point, and set all that equal to 0. So I get an x plus a 1 plus a 2y minus a 1 plus a z minus a 1 is 0. So I get x plus 2y plus z, and I guess I can move the 1 over to the other side. There it is. Any questions on getting the equation of the tangent plane? All right, so let's check this out. So we can, well, let's see. GeoGebra is good for this because it can plot the vectors. I haven't quite figured out how to plot the vectors yet in the three-dimensional Desmos. So here's GeoGebra. We're going to go down to 3D Calculator. Now we'll see if GeoGebra handles this implicit function. The nice thing that Desmos has over GeoGebra is that it's good at doing implicitly defined functions. So this is not. So what we're going to have to do here is we're going to have to solve for z. If you don't care about plotting vectors, then Desmos is going to be a better option for these graphs. But so there we go. We're going to look at our point P. That was negative 1, 1/2, 1. So there it is, and let's make it a different color here. So it pops. There we go. Okay, there it is, right there on the surface. Now we're going to put in our normal vector here. What was the vector? 1, 2, 1. And then we're going to translate that vector. So I'm going to take that off, and I'm going to translate the vector from a point. So we'll pick the point. Wait a minute. We got to keep this on for a minute. There we go. Vector from a point. There's the point. There's the vector. There it is. Okay. Now we'll take this off. So that's the gradient. Oh, it flipped over now. There we go. Okay. So you can kind of see there the orthogonality to the surface. And now we'll type in our plane rather, x plus 2y plus z equals 1. There it is. And if you want, we can, I think that's pretty good. We can change the color here. We'll make it red as well. And then you can kind of observe there that local linearity. So if I kind of turn it there, I think you can see it. Now on Desmos, once again, you can get on Desmos. I don't know how to do the vector on Desmos, but Desmos seems to handle these implicitly defined functions much better. Just gotta use parentheses. So if all you're looking at is the tangent plane and local linearity, this will do the job for you. You can see the local linearity there. You can zoom in. So Desmos renders things a lot nice, more smoothly, I think. Okay, but there it is. There's your local linearity. Okay. All right. Now, we had a tangent plane before, though. So recall, if z equals f of x, y is differentiable, then we had the tangent plane equation here. Z was equal to f at a, b, which is your initial z value, plus your rate of change in the x direction times x minus a, plus your rate of change in the y direction times y minus b. So it's like you're starting at f of a, b, you're doing a linear approximation, you've got the correction in the x direction plus correction in the y directions. That was our thing there. And so the question is, if we've kind of generalized tangent plane formulas, we should be able to recover this in the special case z is a function of x and y. And so this is a classic kind of thing we can do. If we look at z equals f of x, y, we can rewrite this equation as z minus f of x, y equals 0. And I can think of this surface as the level surface of a function of 3 variables. It's a level surface where this is equal to 0. So this is what's happening here is this equation, z is the dependent variable, x and y are independent variables. Here, x, y, and z are all independent variables. So we're taking a step back and looking at this relationship between z, x, and y as being a level surface of a relationship where x, y, and z are independent. Okay, so we're taking a step back. And now what I'm going to do is look at the gradient of this function. So once again, in this formulation, x, y, and z are all independent. So if I wanted the partial derivative of capital F with respect to x, I'm going to take the derivative of this expression, treating x, y, and z as independent, which means as far as x is concerned in this formulation, z is a constant. So the derivative of z with respect to x would be 0, and I would just get minus whatever the derivative of this is with respect to x. So likewise, what would we get if we took the partial derivative of capital F with respect to y? So once again, in this formulation, we're assuming x, y, and z are all independent. So if I take the derivative with respect to y, very good. The z would drop out. I get a minus fy xy. And finally, if I take the partial derivative with respect to z, what would I get for this? Yeah, just 1. So my gradient here is the vector minus little fx minus little fy and 1. And if that vector looks familiar, it should. So if we want a little bonus here, go back and check out where this vector came up before, because it came up, was it just last week? Yeah, so go back and look. This came up before. This vector, we've seen this vector before. And spoiler alert, this vector comes back. All right, but there's that vector. Now check it out. If I'm looking at the point on the surface a comma b comma f of ab, and I look at the gradient of capital F, I would get minus fx at ab minus fy at ab, 1. And so to get the tangent plane, what would I do? You take the x component times the change in x plus the y component, which I guess would be a minus then. The y component of the gradient times the change in y plus the z component of the gradient times the change in z, and that would all be equal to 0. So that would be how to get the tangent plane using the gradient. So look what happens if I solve this equation for z. So I'll recopy this over here. So you can see what happens. I've got a minus fx ab times x minus a minus fy at ab times y minus b plus z minus f of ab, all equal to 0. If I solve this equation for z, I'd add over the f of ab, I'd add over the fx part, and I'd add over the fy part. And sure enough, that's the formula we came up with a week or so ago. You follow? So it works. So once again, that's a big theme here in Calc 3 is if we understand 2 variables, to go to 3 variables we tack on a z. Anytime we generalize something, we double check that it specializes back to what we know from before. Okay? Now I suspect some of you were using these kinds of calculations. Once again, I don't know what, I think some of you have your own sources for Calc 3. But some of you were using this formula. Which one here? Yeah, some of you were doing tangent planes like this well before we even talked about the gradient, using some different formula. That's where it comes from. All right. I always get a little nervous when students use formulas we don't talk about yet in class because I don't know if they know what they're doing or not. But there you go. Now you know. And so there's your homework for that. Once again, some out of 15.5, some out of 15.6, because we went a little bit out of order. So we go back and pick up some stuff from the 15.5.